All right, so mission 5. Let's talk about mission 5. What's the deal with mission 5? See, these are the problems I assigned. Got some tea. Let's see here. So, yeah. I think I solved everything, even though you guys could pick 2. Let's just get into it here. So, problem 47. So, I know, I'm not sure all of you have had differential equations, but honestly, I think the differential equations that we encounter here, they're not bad. Like, you probably can figure them out just on Calc 2 basis. But anyway, now that I'm sharing the solution with you, the solutions should be pretty easy to find. So, I'm an idiot. So to find the flow, we find the integral curves and then use them to construct the flow. That's what's done. So I find the integral curve through an arbitrary point, basically. And to do that, I make the velocity vector field, the velocity field of a curve, match the given vector field. And so v at gamma of t must be equal to d gamma dt, but I'm using x and y for the components of gamma. So for this one, that means I need dx dt to match y, and you need dy dt to match 1. All right? So that gives me the differential equations dx dt equals to y and dy dt equals to 1. So as a general rule of thumb, when you're confronted with a system of differential equations, or if you run into well, I don't know. They say that if you're mugged by a bunch of bullies, you should like pick the biggest, meanest one and beat him to a pulp first. It's a general rule of order, but it seems like it would be easier to beat up the weakest one first. But I guess I could see how that would go badly. So I guess differential equations not the same as street logic for taking on groups of thugs. Oh well. Who knew? So I'm going to solve the easiest one first, and then so dy dt is 1, so that gives me y is equal to y naught plus t. I might as well build the initial conditions into it, because like just think about it. When time equals 0, I want to have the point y naught. I'm just pointing, I'm making x naught y naught my, I want that to be where t equal to 0 is. That's my approach. Now, once I have y naught plus t as my solution for y, I put that in for y here, and then I can integrate both sides, and integrating gives me this. And again, if I put t equal to 0, that drops this and that out, which means whatever else I have better be x naught. So here's my integral curve for the vector field through x naught y naught, and then from that I build the flow. The flow tau sub t of xy, which tells me if I start at the point xy and I want to flow along an integral curve, unit time t, then I just do this. And so you see how the formulas go. Just change y naught to just y and change x naught to just x, and that gives you the flow. All right, so that's how you do it. So basically, if we can solve the differential equations, we're good to go. Which I think for the problems in this book, it's not bad. And so here's another one, like this vector field. We get dx dt equal to x, dy dt equal to y, but you should recognize that as being the exponential and the exponential 2t solutions. If you don't believe me, separate and integrate and fit the initial condition, but I'm content to write down the solution and notice that if I plug it back in, it works. And so there's your flow. This one, we've got dx dt is x and dy dt is minus y, which gives me positive and a negative exponential and gives me that flow. All right? Yeah. Great. Next up, let's see here. And of course I could make a mistake somewhere here, so if you feel like you're doing something different, if you're following the same general procedure, you might be right, who knows. So here I've got, notice the switcheroo, partial y and partial x, right? So dx dt is y and dy dt is x. If I plug this one into that one, I get d squared y dt equals y. A function which behaves like that is hyperbolic sine or cosine. And, oopsie, I was going to erase that. Do 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 doodly do 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 do. Come on. Oh, this doesn't have long to live. Yeah. Maybe it's. Yeah. Maybe it's. Yeah, it survives. All right. So if I put this as my solution, you can easily check that twice differentiating this gives you back it again. And also, if we plug in times 0, we get y naught. And if x is equal to dy dt, then that forces x to be this. And then what is c2? Well, x of 0 is equal to c2, which is x naught. So lo and behold, there's my integral curve through x naught y naught, which suggests that the flow is this. So there you go. Now problem 48. Problem 48 is really cool. Because I don't think I've ever done this calculation before, and it's pretty neat. So the idea is you're given vector fields, and the question is, can you construct a coordinate system which realizes the vector fields as coordinate derivations? Of course, if the vector fields do not commute, game over, end of story, you can't do it. Because, if you can make them into coordinate derivations, then the Lie bracket is 0. So if the Lie bracket is non-zero in a Cartesian coordinate system, then it's going to be non-zero in this new hypothetical coordinate system, which means a contradiction if they're actually going to be coordinate derivations. So that's why I check that the vector fields have that are commuting under the Lie bracket to start with, and then for this one I just write down. Because I think you can just write down. After the previous problem, I was able to just write down. The flow of this one is that. The flow of that one is this. And as such, if I look at phi of st, is eta t composed with theta s. So what this is doing is it's basically saying take this point, flow s along the theta direction, the theta flow, and then flow t along the eta flow. And that gets you to the point that would correspond to s comma t, taking 1, 0 as the origin. So that's pretty neat. And I'm just following the book method. Example 9.47 in the book. I'm using that to come up with a solution here. So, all right, continued. Let's see here. So that was my phi, x, y. Now I solve for s and t. I get t is equal to that, s is equal to that. So as that suggests, putting s1 equal to x minus y minus 1, and s2 equal to y. So that I think these are going to be my coordinates that I claim, and then so I just double check it. Partial s1 by the chain rule is this, which if you have x is that and y is that, when you calculate the partial derivatives you get 1 and 0 respective, which means partial s1 is x. And S2, on the other hand, is partial x plus partial y as desired. Now, it's kind of funny because you might think that because you want S1, you want V1 to be partial S1, you might think, and V1 is just, partial x, you might think that you should make s1 equal to x. But it's not the case. It's just not the case. See, because partial derivatives, it's not just about one thing or the other. They're taken in conjunction. And so like partial differentiating with respect to s1 only makes sense as much as you've defined s2. Right? I mean, so like every s1 derivative, partial 1 derivative is done holding s2 fixed and vice versa. Anyway, so it worked. And then this one, I really wanted b to be non-zero because I'm tired at this point, but it was 0. So I have to find the flow of this thing, which I haven't done yet, and it's not obvious to me. So I'm solving this differential equations for V1's flow and these differential equations for V2 flow. I need both of those to build my phi, to build my new coordinate system. All right, so So I do that, I solve, and I get this. As you can see, I made some sign errors along the way. It took me a bit to correct it, but I got it. And then because like when I first did it, and I went to calculate my phi of st, it only involved one variable. I'm like, uh-oh. Definitely the s and the t should appear in the formulation, otherwise it's not right. Anyway, calculate the flow for v1, calculate the flow for v2, put them together, start at the point 1, 0. You could start anywhere, by the way. We're just making 1, 0 the origin for the st coordinates, basically, which I'm then calling s1, s2 to be, it's really ts, because the t came, anyway. So I've got that as my quote-unquote phi map, and then solve for x and rather solve for s and t. I get that, which then gives me s plus t is log and s minus t is log of that. And if I add or subtract those, I get this for my s2 and that for my s1. And as a check, when you calculate partial s1 as such, you get this and that and that and that, which is what we wanted. And I double checked also down here, partial s2 does in fact work out as I claimed. So hooray! You can do the math. That's pretty neat. Because one thing to ask hypothetically, like, can the vector fields be written as coordinate derivations? It's quite another thing to actually be able to find explicitly the coordinate system which makes that happen. That's pretty neat. Pretty neat calculation. Now finally for part C, he threw me a bone, and the Lie bracket was non-zero finally. V1 and V2 is that which is non-zero, consequently. If I miscalculated here, that might be interesting, because then we'd have 3 coordinates, so we'd have to do the composition of not 1, not 2, but 3 flows to get the phi of S1, S2, S3, and then blah, 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 same kind of thing. Problem 49 is next. Problem 49, we've got x and y. Supposed to find the flow and the flow, so we do that. I find this flow and that flow. I look at the flow one way, I look at the flow the other way, and I get different looking results, and yet both of them have x, y at 0, and yet they're not equal. And the reason for that, the flows not being equal, is that these are not commuting. The Lie bracket of x and y is non-zero. So, yep. This is problem 918 from Lie. These are all problems from Lie, pretty much. Oh, yes. This was, like, I don't know, stupidly easy after the other stuff that I've assigned you guys. Good grief. So here we define the dual map, or the transpose of A, to be a mapping on the dual spaces if A is a linear map on the vector spaces. And the way that's defined is that A dual on omega, if it acts on V, is omega of AV. And so here I prove first that the dual of A acting on omega is in fact a dual vector on V, so that proves that the map A star is in fact into. It's as claimed, it really is giving you V stars, really is giving you dual vectors to V, and that's this. And I had to use the linearity of A, the fact that omega itself is linear on W, and of course the definition of the dual map. And then also I had to prove linearity of A, which is to say that when I put in omega 1 plus C omega 2, I can get out A star omega 1 plus C A star omega 2. Now this is holding for all V, therefore it follows that these are equal, which is to say that A dual is a linear map, as claimed. What's cool is if you sort through the, if you have a basis, beta, and a mapping like from, say, V to V, and you use the basis beta matrix, I think it may actually work if I have basis beta for V, basis gamma for W, and then for the dual map I have like basis gamma star and basis beta star, where those are the dual bases. It is in fact true that the matrix of the dual map with respect to these dual bases is the transpose of the matrix with respect to the original bases. That's kind of neat if you sort through it. That was not in your homework, but I've worked that out before. And then here we have the socks shoes property for the dual, which is, true for these reasons. And that the dual of the identity is the identity, actually. So yeah, those are pretty straightforward calculations. I'll let you look at them. I mean, I say straightforward, but it does take a second to get used to the definition of the dual map here, admittedly. And then here is the double dual canonical isomorphism, and the proof that it is in fact into the double dual, and that is in fact linear. Here's the proof of those claims. Yeah. So nothing especially exciting there, but these are fun. So proving the properties of the differential basically all follow immediately from corresponding properties of the derivation. Because dpfv is v of f and v is a derivation, for part A, that linearity of v gives me a linearity of the differential construction. Then the product rule, the fact that v is a derivation, Leibniz rule, right? That gives me the corresponding product rule for the differentials. For part C, if I let h equal to fg, if I take the differential of f, it's the differential of, g dh plus h dg by part B. And then if I solve for dh, I get the formula, which is, so essentially, deriving the quotient rule and the differential formalism. And then I wrote a little bit more for D, basically just to say, hey, we've got a chain rule for the differential because we've got a chain rule for the derivation. And that follows because we've got a chain rule for regular derivatives on Euclidean space. So if any of these is more convincing to you than the other, well then great. And if not, I'm sorry, but here's a argument to support the chain rule. Assuming, of course, that we know the chain rule from like advanced calculus, which we might know. But anyway. And then this one, problem 54, is actually really easy if we read the chapter we skipped, corollary 10.20 from page 259, where we learn that a smooth vector bundle is smoothly trivial if and only if it emits a global frame. So if Tm is trivial, there's a global frame for Tm. But the thing is, if you got a global frame, you can find the dual to the global frame, because that's just linear algebra pointwise. And so you got a dual global frame, and that's a global frame for T star m, which then means T star m is trivial. And conversely, if you have T star m is trivial, you got a global coframe, which you can dualize to get a global frame, which then gives you that Tm is trivial by corollary 1020. Like I said, it's easy if you've got the right theorem in front of you. Problem 55, super fun. So this is just straight pullback calculations. So essentially, you just look for, here's your function that basically puts x equal to this and y equals to that. And you got your omega is x dy minus y dx. That's sort of in the range. And pulling it back to here, it just amounts to changing the x's and y's to st and e to the t. Now, this is just notation to try to express that idea. But basically, when you really look at what's going on here, I just plug in x equals to st and y equals to e to the t into this expression, and you get that. Likewise, down here, we plug x equal to that, y equal to that, z equal to that, into z squared dx. Here's some notation to express that idea, but it is ultimately just the substitution of the formulas for f into the form we're pulling back. Likewise here, you've got s. This is your map, and so that gives me x, y, z composed with f to be this, this, and this. And then, so when I take this differential form, covector field, and I pull it back under f, then I just plug in s for x, t for y, and z, that root, which, using the calculus of differentials we just went through, chain rule, 1 over twice the derivative, like so. And, well, that just gives me this, so yeah. Woohoo! Yeah, great. And then, is it true? Are we to the final problem? Yay. So I'm not entirely confident that I've integrated correctly, guys. Because I was tired, and when I got to this problem. But anyway, here it is. To calculate the integral, we just plug in, basically pull back omega under the mapping f of t is t. So x equals to t, y equals to t, z equals to t. You plug those in, and of course dz is dt, dy is dt, dx is dt in this case. So I'm just literally replacing x, y, and z with t into this expression, and, collapsing it all down, and I get this, which gives me that. Which, if I haven't made a mistake, gives me, and if you got something different, you can double check me against Wolfram Alpha or whatever, it's fine. But I got 2 times 1 minus log 2, and again, I'm not, whatever. This was worse. The eta one gives me this horrible integral, which I have calculated, but I think I made a mistake in here somewhere. I don't know where exactly, but I got, I got this down here eventually, and like I said, I don't believe this integral. There's something wrong in here somewhere, I think. And the reason I think that is because for part B, when I decided if omega or eta was exact, so when I tried to solve the potential equations for omega, right, try to find an f such that df is equal to omega, well, that's tantamount to being partial f partial x being the x component of dx, partial f partial y the coefficient of dy, partial f partial z being the coefficient of dz, so this, when I differentiate that with respect to x, I get this. With respect to z, I get that. But when I differentiate this with respect to x, I get that. And these are not equal, therefore, it cannot be the case that omega is the differential of a potential function in this case. So what about eta? Well, eta, on the other hand, when I sort through the partial integrations, I get this, I get that. I'm like, wait a minute, that's enough. If I do 2z over this plus log of that, then df is equal to eta, so it's exact. Yay! Away from the origin, of course. And then, as such, I can recalculate the integral over the curve from 0, 0, 0 to 1, 1, 1 as being just f of 1, 1, 1 minus f of 0, 0, 0. Of course, f of 1, 1, 1 is 2 over 2 plus the log of 2. And then 0, 0, 0 gives me 0 for this one, but this one also gives me 0. So I get just 1 plus 2 over 2 plus log. So I get 1 plus log 2. So apparently I have miscalculation in part A. Because I think I trust this calculation. I'm much less trustful of what I did in the other part. But on the other hand, I'm done. Like, that's it. I've had enough for mission 5, and I'm sure you probably will have also had enough by the time you've seen this video. But anyway, I hope that helped you guys learn these things. That is the goal, of course, and so I'll hopefully make an announcement sometime soon with a little bit more breakdown on like the what's on your midterm. Some obvious things. I would just say I would expect there's a push forward. I would expect there's a pullback. I would expect. Well, anyway, I'm going to stop there. There's probably a calculate the Lie algebra problem, right? Because that's kind of a fun calculation that I think after you get through it, it's not that bad. Show something's a submersion, show something's an immersion. No, so the rules for like your formula sheet is you guys can have all the definitions. You can write on all the definitions known to mankind. That's fine. And you can even write examples. That would be fine. I just don't want you to write any proofs. All right, so please no proofs. You can write theorems, you can write definitions, you can write examples, but I would ask no proofs because I might ask you some proofs. So, and if you just have the proofs written down on the page, that becomes rather silly, and I don't really want to do that. So anyway, thanks guys. Enjoy your break.